Hello students, welcome to BTech first year bridge course. In the last lecture, we have discussed about curl of magnetic field, and from there we have established Ampere's circuital law for steady currents. Now today we will discuss magnetic potential. Now similar to electric field, related to electric potential, magnetic field can also be related to magnetic potential, and they are of two types. One such potential is magnetic scalar potential and another one is magnetic vector potential. So at first we will try to understand what is magnetic scalar potential. Okay. So we know that in electrostatics, electric field is derivable from electric potential, right? Now how? So as you know, curl of electric field is 0. So why? Because electric field is irrotational field as well as conservative field, right? So electric field can be written as minus of gradient of electric potential, right? Now the importance of this equation is that the electric potential V is a scalar quantity and it is easier to handle than electric field because electric field is a vector quantity. So one has to work with magnitude as well as direction, right? Now similarly in magnetostatics, magnetic scalar potential can be obtained from this equation, which is called differential form of Ampere's law, and here J is the volume current density, right? Now in regions of space where free current is absent, means current density J is 0. So curl of magnetic field will be 0, right? Therefore, magnetic field can be expressed as the minus of gradient of a scalar quantity which is called phi m. And here the minus sign is considered because the scalar quantity phi m decreases along the direction of the magnetic field. Okay. So this scalar quantity phi m is called magnetic scalar potential. Thus, you can see that magnetic field can be derivable from the gradient of magnetic scalar potential. Now, how can you get an idea in realistic way? You know that in magnetic material, one can have magnetic moment and it actually creates magnetic field, which you can write as gradient of some scalar field phi m. Okay. Now since divergence of magnetic field is 0 and magnetic field is expressed as minus of gradient of scalar potential, we get Laplace's equation in magnetostatics, which is del square phi m equal to 0. Now the solution of this equation will give us magnetic scalar potential. Okay. So here del square is called Laplacian operator, which we have already discussed in electrostatics, right? Thus, we can conclude that Laplace's equation in magnetostatics is valid only outside the magnetic sources and away from currents. And magnetic field can be calculated from the magnetic scalar potential using solutions of Laplace's equation. Okay. Now let's discuss another potential, which is magnetic vector potential. we have seen that magnetic scalar potential is useful only in the region of space away from free currents, right, where current density is 0. Then magnetic field, or more precisely magnetic flux density, can be computed from magnetic scalar potential. Now the potential function which overcomes this limitation and useful to compute magnetic field in region where the current density is present, and this is called magnetic vector potential. Okay, so magnetic vector potential is useful to compute magnetic field in region where current density is present, but magnetic scalar potential is useful to compute magnetic field in region where current density is 0, right? So this is the difference. Now let's see how to relate magnetic field with magnetic vector potential. So since divergence of magnetic field is 0, magnetic field can be written as curl of a vector A, and here A is called magnetic vector potential. So you should remember that a solenoidal vector field in physics can always be written as the curl of some other vector field. Okay. Now the form of the vector potential can be obtained from Biot-Savart law. Now let's see that. Now according to this law, the magnetic field at any point here P due to a volume distribution of current is like this. Here this is called source point and this is the field point. Now since gradient of 1 by r is minus of r vector by r cube and curl of j by r is gradient 1 by r cross j plus 1 by r curl j, we can write this j cross r by r cube as like this. So here j cross r, what is happening? J cross r by r cube is basically minus of j cross gradient 1 by r, and then if we change the vector sequence, we get gradient 1 by r cross j and minus sign is absorbed, right? Now if you use this vector identity, curl j by r equal to gradient 1 by r cross j plus 1 by r curl j, we get this curl j by r minus 1 by r curl j. Now since the current density j is with respect to source point coordinate and del operation is with respect to field point coordinate, curl j will be 0. Okay, then we are left with curl of j by r from here to here, and we get this alternative form of magnetic field, right? So here you should note that we have pulled out the del operator from this integration. Now this is allowed because del operation is with respect to field point coordinates and the integration is with respect to source point coordinates. Okay. Now since the magnetic field is curl of magnetic vector potential, and comparing with this alternative form of Biot-Savart law, we can obtain the magnetic vector potential like this for volume current distribution, right? And by analogy we can write this form of magnetic vector potential for a line current distribution, and this is the form of vector potential for surface current distribution. Okay. So using these forms of magnetic vector potential, one can find out the magnetic field. So this is the importance of magnetic vector potential. Okay. So this is the last lecture of this lecture series of module 4 of bridge course. Now I am sure you have learned many new topics from this lecture series and new ideas in electrostatics as well as magnetostatics. I also feel that the way I tried to represent it will change your thought process to some extent and it will help you in the main course, right? Okay, so thank you for attending this course and all the best for a great future ahead.